Okay, so in the last video we talked about the first derivative test, and we talked about what it says and why it works. So now we're going to talk about how to use it. So this is basically if you want to find extrema, so that means mins and maxes. So this will work for local or relative mins and maxes, and this process that we're going to talk about, it also works as part of a larger process for global mins and global maxes. So basically, if you want to find global mins and maxes, or absolute mins and maxes, same thing, then you have a longer process to follow, but it involves exactly this. So anyway, we'll talk about that in a later video, but for now, and for the next few videos, we're going to do local mins and local maxes. And so that's the same thing as relative. So remember, local, relative, same thing, and global and absolute are the same thing as each other. But anyway, so if you want to find local mins, local maxes, steps to follow. Step 1, find all the critical points of the function f of x. So remember, a critical point is a value of x where the derivative is 0 or the derivative is undefined. And remember that value of x also has to be in the domain of the original function. So step 2, make a sign chart for f primed of x, the derivative. So we talked about sign charts a few videos ago. If you didn't see that video, or if you don't remember too well, don't worry about it. We'll talk about it again here as if it hasn't been brought up before, just as a refresher. So step 3, determine the sign of the derivative in each interval. So your sign chart is basically going to have a bunch of intervals on it, and then step 3 is determine the sign of the derivative in each of those intervals. So, but we'll see that with our example here. And then step 4, apply the first derivative test to find the extrema. So once you've gone through these 3 steps here, you basically just apply the first derivative test that we talked about in the last video to find your extrema. Remember, extrema is just a fancy word for mins and maxes. So, all right, let's see an example here. And as we do the example, we'll refer back to these steps to see how the process works. So example 1, find all local extrema of f of x equals x cubed minus 3x. All right, so we want to find all the local mins and local maxes of that guy. So whenever you do a problem like this where you have to use the first derivative test to find mins and maxes, or really just any kind of problem, no matter what you're using, to find mins and maxes, the first thing you want to do is take a derivative, right? Because we have to find critical points, and in order to find critical points, well, we need the derivative to do that. So the very first thing we do is take a derivative. Okay, so if f of x is x cubed minus 3x, well then what's f primed of x going to be? So f primed of x is going to be, well, just from the power rule, is going to be 3x squared and then minus 3. Okay, so the derivative is 3x squared minus 3. Okay, so that's our derivative. Now, step 1 says find all the critical points. So we take this derivative and we have to find where is this derivative 0 and where is the derivative undefined. So first we want to find, all right, where's the derivative 0? So we're going to take the derivative and set it equal to 0. And we're just going to solve this equation. So there's a common factor of 3 we can pull out, so that's going to be 3 times x squared minus 1. So most people watching this video are probably pretty comfortable solving this quickly, but I'll show you the details just in case. So divide both sides by 3. Okay, so this 3 is basically gone. So we have x squared minus 1 equals 0. So there are a bunch of different ways to solve this. Some of them are kind of overkill, much more than you would need to do. So we could factor this, we could add 1 to both sides and then take the square root of both sides, which is probably the simplest method, but you have to be careful. Or we could use the quadratic formula, which is totally overkill, or complete the square, which is insanely overkill. Anyway, let's factor this, just because that's probably the safest. So remember, this is a difference of squares, right? X squared minus 1, 1 is the same thing as 1 squared, so difference of squares, it's x minus 1, x plus 1 equals 0. So from here we get x equals 1, and from here we get x equals negative 1. Okay, so x equals 1 or negative 1. Okay, so those are the values of x that make the derivative 0. Now we also have to figure out, all right, where's the derivative undefined? Well, the derivative is just a polynomial, right? It's just a nice little quadratic function here. Oops. So there is no value of x that makes this guy undefined. Okay, in other words, any value of x you put in here, nothing crazy is going to happen. It's not going to be undefined. So there are no critical points where the derivative is undefined. So these are the only 2 critical points we have. X equals 1 and x equals negative 1, the only 2 critical points. All right, so that was step 1, find all the critical points. All right, so now we found them all. Now step 2 is make a sign chart for f prime of x. So again, if you don't remember what the sign chart is, or if you just didn't see the video, if you're not sure, then we'll talk about it here. So a sign chart, first, we just draw a number line. Okay, here's a number line, just a horizontal line with arrows on both ends. And then every time you draw a sign chart, you always want to label it. Always, always, always label it. Okay, so this is a sign chart for f prime, so we're going to label it f primed. Right, so here's our sign chart for f primed. Now, when you make a sign chart, put all of your critical points on there. The only critical points we have are 1 and -1. So -1 goes further to the left because it's smaller. Okay, so -1 to the left, 1 over here because the numbers increase as you go to the right. Okay, so -1 and then 1. So that's it for step 2. Make a sign chart for the derivative f prime of x. All right. So now step 3, determine the sign of f prime of x in each interval. Okay, so the sign of the derivative in each interval. So how do we do that? Well, we pick one number from each interval and we evaluate the derivative there and we see, is the derivative positive or is it negative? Okay, so in this interval, well, first of all, what are these intervals here? Well, here, I'll write these down real quick and then erase them. So here, all the numbers to the left here are less than -1. So this is x is less than -1. What about in this interval here? -1 is less than x is less than 1. Okay, in this second interval here, x is between -1 and 1. In this third interval, x is greater than 1. Okay, these are all the numbers greater than 1. These are all the numbers less than -1, and these are all the numbers between -1 and 1. So we have these 3 intervals here. So we pick one number from each interval to test the derivative. So let's just pick -2 from here. Okay, we can pick anything really, like -2.5, -33, -10, -4 billion. Some of those are pretty crazy, but they'll still work. But -2 is a good one because it's in this interval. It's pretty simple. It's not too crazy. Numbers won't get too bad. So anyway, let's do that, and let's erase these here. So we're going to pick x equals -2 from that interval, and we're going to evaluate the derivative there. So let's do that. F primed of -2 equals what? Well, here's f primed of x. Okay, so f primed of -2 is 3 times the quantity -2 squared, then minus 3. Okay, so this is 3 times -2 squared, and then minus 3. All right. -2 quantity squared is +4. Okay, so this is 3 times +4 minus 3. 3 times 4 is 12. 12 minus 3 is 9. So this equals 9, which is positive. Okay? So that means the derivative is positive in this entire interval. Now, in case you're thinking, well, wait, we only tested it at one number. How do we know it's positive everywhere? Well, because here, the only place where the derivative could change sign is at a critical point, right? So, because remember, a critical point is a possible local min or a possible local max. So a critical point is the only place where derivative could change sign. So here, that means if the derivative is positive at one point here, then the derivative has to be positive everywhere in this interval. Because if the derivative changes to negative again, then because the derivative is continuous, then if the derivative goes from positive to negative, it had to move through 0 somewhere because it's continuous. Okay, it would have had to have moved through 0 somewhere. But we know the only places where the derivative is 0, that's here at -1 and here at +1. Okay, so the derivative is stuck being positive in this interval over here. Okay, so here x is less than -1 means the derivative f primed is always positive on this interval here. Okay, because the only place where the derivative is 0 is here and here. So the only place where the derivative could change sign is here and here at -1 and 1. So basically the derivative is just stuck being positive in this entire interval. It can't cross 0 until it gets to -1. We found that out when we solved for the critical points. Okay, so anyway, that's just a little side note there. So that's why it's okay to just test at just one point, because in that entire interval, the derivative is stuck being the same sign. The derivative can't change sign in that interval. Okay? And that's why it's also important to make sure you find all the critical points. Okay, so here's all the critical points here. And these are the only places where the derivative might change sign. So, in the second interval, let's pick 0. Okay, 0's in here, right? It's between -1 and 1. Numbers like 1/2 or 2/3 or -4/5, those will also work. They're kind of bad ideas. because the math will get kind of messy, but they'll still work out. But 0, if you can pick it, is a good one. So let's do 0. So f primed of 0 equals 3 times 0 squared minus 3. Okay, so that's, I'll come back down here. 3 times 0 squared minus 3. Now, 0 squared is 0. 3 times 0 is 0. 0 minus 3 is negative 3, which is negative. So negative 3 is less than 0, so we go back up here and we say, okay, so the derivative has to be negative in this entire interval, right? For the same reason we just talked about for this interval. Okay, the only place where the derivative could change sign is here and here. Now that doesn't mean it has to change sign there, right? The derivative might be positive, or the derivative might be negative here too, right? It's possible, but it's the only place where the derivative might change sign. So here the derivative is stuck being negative in this whole interval here, and it's stuck being positive in this whole interval here. All right, so now let's test the derivative here. So let's pick x equals 2. 2 is a good number to pick because it's in this interval here. It's not too big. Won't get too crazy. So now we find f primed of 2. F primed of 2 is what? It's going to be 3 times 2 squared minus 3. So this is 3 times 2 squared minus 3. 2 squared is 4. 3 times 4 is 12. 12 minus 3 is 9. So this is 9, which is positive. Okay? So that just means that the derivative is positive in this whole interval up here. Okay, so first I want to point out, if you're wondering, is there any significance to this is 9, this is negative 3, this is 9 again. Is there any significance to what these numbers are? No, not really. It's just kind of a measure of how steep the function is. So 9 means the function's increasing, with a rate of 9 at this one particular point. But we'll talk more about that when we get to some physical applications. But anyway, there's no significance to this number other than the fact that it's positive. There's no significance to negative 3 other than the fact that it's negative. There's no significance to 9 here besides the fact that it's positive. So that's all we care about is where's the derivative positive and negative. We don't care about these exact values specifically. Just want to point that out real quick. So anyway, that's it for step 3. Determine the sign of the derivative in each interval. So we just did that. Now we go to step 4, apply the first derivative test to find extrema. So remember, the first derivative test, we talked about what it says in the last video. So here, let's apply that here. So what do we see here? Let's look at negative 1. Just to the left of negative 1, the derivative is positive. Just to the right of negative 1, the derivative is negative. So the first derivative test tells us that we have a local max at x equals negative 1. So remember, the first derivative test says if the derivative is positive to the left of c and negative to the right of c, then you have a local max at c. So that's happening here. Positive derivative to the left, negative derivative to the right. So this point right here at x equals negative 1 has to be a local max. Okay, so a local max at x equals negative 1. All right. So now this function, or sorry, not the function, but the example says or the instructions say to find all the local extrema. So here we just found where it occurs, right? We found there is a local max at x equals negative 1, but what is it? If we want to know what it is, remember the y coordinate or the y value of the function, that's what it is. Okay, so we know where it is. Where is, that means the x coordinate, right? So where is the local max? Well, the local max happens at x equals negative 1. What is it? Well, if we want to find what it is, then we have to take negative 1 and put it back into the original function. So be very careful with that. Put it back into the original function, not back into the derivative. Okay. So it's a common mistake that happens every now and then. So don't put this back in the derivative. Okay, this is the critical point, right? So we know the derivative is 0, but we want to know what is the local max? What is the actual value? And the value is given by the original function. Okay, we're talking about mins and maxes of this function here. So we want to know what is the min, what is the max, where are the mins, where are the maxes, things like that. We know where there's a max, there is a local max at x equals negative 1. Now we want to know what is it, and to find out what it is, we put negative 1 back into here. So let's do that. So f of negative 1 equals negative 1 cubed minus 3 times negative 1. Now, negative 1 cubed is just negative 1. Minus 3 times negative 1 means plus 3. Negative 1 plus 3 is 2. All right, so this is the value of the local max. So the local max at x equals negative 1 is y equals 2. All right, so that's, we're almost there. Now we have to look at this other critical point. So now at this critical point, x equals 1, what happens? What happens just to the left? Just to the left, the derivative is negative. Just to the right of x equals 1, the derivative is positive. Okay, so notice over here the derivative is positive, but we don't care about this. We don't care about that because all we care about is what's happening just to the left and just to the right. So we can cover up all this other stuff here. And we see just to the left, the derivative is negative. Just to the right, the derivative is positive. And the first derivative test, okay, we're on step 4, the first derivative test tells us, okay, negative derivative just to the left, positive derivative just to the right, then that means we have a local min here. Okay, local min. So local min at x equals 1. And what is it? Well, to find what the actual value is, we do the same thing we did up here. We take x equals 1 and put it back into the original function. Okay, because we're talking about mins and maxes of this function here, of the original function f of x. So we take our x values and we put them into here to get the corresponding y values. So f of 1 is 1 cubed, okay, 1 cubed minus 3 times 1. So this is 1 cubed minus 3 times 1. 1 cubed is 1. 3 times 1 is 3. 1 minus 3 is negative 2. So the local min is negative 2. Okay, we just found that out. So it happens at x equals 1, and it is negative 2. So the local min at x equals 1 is y equals negative 2. All right, and that's our answer for this problem here. So, your instructor or whoever, your professor, and so on, they might want you to answer in a different way, but this is just kind of, this is probably the most thorough way you can say. So here's where local max happens, and here's what it is. Here's where the local min happens, and here's what it is. So remember, if if you don't remember the first derivative test for the last video, or if you didn't watch it, I recommend checking out that video and just watch it real quick. And here, so remember, positive derivative means increasing function. Negative derivative means decreasing function. So what does this really mean? This means that the original function f increases until x gets to negative 1, then the function starts decreasing again. Okay, so that means function increases then decreases, so it went through a local max. And here the function decreases and then increases again, so it went through a local min. So remember, function is increasing, function is decreasing, function is increasing, because the derivative is positive, negative, positive. So that's, that's really the key to all of this. You don't have to remember the whole statement of the first derivative test. So that stuff we said in the last video, you don't have to remember it word for word or anything. Just remember, positive derivative means increasing function. Negative derivative means decreasing function, because derivative is the same thing as slope. All right. So that's really, that's the key to this whole thing here, the first derivative test. That's kind of the important thing to remember. If you remember that, and if you practice with enough examples, it'll become very intuitive, and it really won't be that difficult at all if you practice enough. And just remember that positive derivative, increasing function, negative derivative, decreasing function. So just, as a check, if you want to toss this into a graphing calculator, you can see what it looks like, and you'll see that the function, so let's erase some of this here. The function, let's set up a coordinate axis here. So x-axis, y-axis. The function is kind of sort of going to look a little bit like this. So it increases, then it decreases, and then it increases again. So if you want to toss that to a graphing calculator, you'll see the function kind of looks like this. So this is y equals 3x squared minus 3. So this is this function here. And then this is negative 1. This is positive 1 right here. So, you'll see in your graphing calculator that the function increases up until x equals negative 1. Then the function starts decreasing again on this path right here. And then once it gets to x equals 1, the function turns around and starts increasing again. Okay. So here, positive derivative, negative derivative, and positive derivative again. Okay, so we see that here, positive derivative, negative derivative, positive derivative, increasing function, decreasing function, increasing function. So just remember that and practice with enough examples and you'll be fine with the first derivative test. So we'll see several more examples in the next few videos. This one wasn't too bad, but they could get a little more complicated, and we'll see some like that in the next few videos. But they all follow the same pattern here, these same 4 steps. So that's it for example 1 with the first derivative test.